Hello, everyone. This is the lecture for Math 210, Section 3.4, Derivatives as Rates of Change. So at this point in Chapter 3, right, we've defined the derivative of a function at a specific point x equal a. Okay, we've grabbed that idea of a derivative at a point and turned it into a function so we can produce functions that give us the slope of the tangent line at any x value that we want, right? And then in section 3.3, we covered a bunch of really handy shortcuts for a certain set of functions that we saw when we were covering section 3.3, right? Okay. So now what we're going to do is we're going to be applying that idea of a derivative to a lot of non-mathy things, okay? There is an interpretation for a derivative. It's actually very important in anything that requires quantitative analysis of anything. And that means physics, that means chemistry, that means biology, that means business. Okay? So let me cover some stuff from before. Okay? So like I said, what we're going to study for this section is in particular the other interpretation of a derivative. And that is this. So the first thing that I mentioned for the derivative is it is defined as the slope of the tangent line, right? Okay. The other interpretation is what I have highlighted here. It is also called the instantaneous rate of change, okay? So now, let me stick in some physics in here, okay? Suppose we had what's called a position function. So suppose I had a function where if I give it a time, it'll give me the position of an object. Okay? Then from the previous class, right, from the previous section, we got this, that the derivative of our position function gives us a velocity. So if we take the idea of a derivative, right, we are doing, what we're finding is the instantaneous rate of change in a position, right? And the other way we've called that before is a velocity, okay? And if we extend it one more time, right? If we take the derivative of the velocity, right, that is the instantaneous rate of change, right, in its velocity. Another way of saying an acceleration, okay? Altogether, we produce this right here, that if you have a position function, its first derivative is going to be the velocity. And if you take the velocity again, right, then you have the acceleration of this object. Okay? All right. So I think the best thing that we can do now, right, is jump into an example. Okay? So one of the first things that you learn in any physics class is the study of kinematics, the study of bodies of motion, the simple motions of an object. Okay? And one of the more important equations is this one right here. This one's the kinematics equation that takes into account an initial position. Let me highlight them as I go through them, right? An initial position, an initial velocity, and an initial acceleration. And if we have those three things, we can define a position function for an object. Okay, so now let's go ahead and do this problem. Suppose we head to the Earth's Grand Canyon, okay? And we know that the gravity for Earth is this, negative 9.8 meters per second squared, okay? And what we're gonna do is we're gonna grab a cannonball and shoot it straight up in the air, okay? We are gonna be on a 250 meter cliff, okay? And the initial velocity when we shoot it out of the cannon is gonna be 50 meters per second, okay? So the first thing that we're going to do is we're going to construct the kinematic equation that describes this vertical motion for the cannonball. Okay, so just picture a cannonball that we point the cannon straight up, right? And we light the match, it fires, and it shoots straight up into the air. Okay, we're going to construct the kinematic equation that gives us the position function. Okay, so for that, we just plug in all the goodies that I gave you. Okay, my S sub 0, my initial height, is going to be the 250 meter cliff, right? So it's going to be 250 plus V naught. That's my initial velocity. I've been given that. That's the 50, right? So it's going to be 50t plus, there's going to be a 1/2. My acceleration is negative 9.8 meters per second squared. And then there's just going to be a t squared. Okay. So this, if I simplify it all down, I get 250 plus, 50t minus 4.9 t squared. Bam. That's it. What I've just done is I've constructed the kinematic equation that describes the motion of this object, of my cannonball, if I shoot it off of a cliff. Okay? Awesome. Okay. Now let's go ahead and do some, we'll start easy. Okay? First of all, I'm going to find S of 2 and S of 10. Good old pre-calc style. Okay? So S of 2, okay, is going to be me grabbing 2 and plugging it into my position equation. Okay? So that's going to be 250. Oh, no parentheses. Plus 50 times 2 minus 4.92 squared. And if you do that all out, you should get 330.4. Okay? Again, S of 10 is exactly the same thing, but I'm going to plug in 10 instead, right? 250 plus 50 times 10 minus 4.910 squared. And if you do that all around outright, 260 meters. Okay, now I'm going to interpret these. They're English words attached to this, right? Okay, so what this one says is at t, at t equal 2 seconds, right? Does that make sense? The height of the cannonball is 330.4 meters. Got it? Okay, and the way that I got that was this, right? I plugged in 2 and the output was this, right? So if the input was 2, that's my 2 seconds. And the output being 330.4, that is the output of the position function. Got it? Okay. Same thing for this one, right? At t equal 10 seconds, right? The height is 260 meters. Okay, same thing, 10 to 60. Okay, so this is what I mean by interpreting. I need to see this English, you grabbing the mathy stuff and turning it into English. Got it? Okay, cool. Okay, moving on. Now I'm going to start playing around with its derivative. Okay, so first thing I'm going to do is find S prime of t. We know what S of t is. That was up here. That was this thing that we found, right? So now I need to take the derivative of that thing, okay? And if you guys remember, right, the derivative of a constant number, that's 0. So it's going to be 0 plus the derivative of 50t, that's going to be 50, right? Minus 4.9, and the derivative of t squared, that's going to be 2t. Okay, so then we have this now. S prime of t is equal to 50 minus 9.8t. All right. Now, I need to interpret S prime of 2 and S prime of 10. Okay, so let me go ahead and do S prime of 2. first. Okay, that is saying, right, I need to plug in my 2 into the S prime, the newly found S prime function that I found, this one, right? So that's exactly what I'm going to do. 50 minus 9.8 times 2. Okay, and if you do that properly, you get, where am I? There we go. 30.4. Same thing, S prime of 10, I'm doing the same thing, 50 minus 9.8 times 10, and that is negative 48. Okay, and now I'm going to put the units on here, meters per second, meters per second. Okay, hopefully you guys see what's going to happen now. I need to interpret these. I need this in complete sentences, right? What we just found, right? The start is still the same, right? At t equal 2 seconds, okay? I'm going to highlight the important bits, 2 and the 30.4, and then the 10, and there we go. Okay? At t equal 2 seconds, okay, 30.4 meters per second. So at 2 seconds, what we just found is the velocity of our cannonball at 2 seconds. Does that make sense? So we can say that at t equal 2 seconds, the velocity is 30.4. Okay? If I interpret the next one, right, at t equal 10 seconds, right, the velocity is negative 48 meters per second. Come on, there we go. Okay, now I want everybody to take a look at this, right? When I see this, right, since it's a positive value, okay, we can assume that our cannonball is still climbing at this point, right? And because this one is negative, our cannonball is falling at this point. Since the velocity is negative, we can say that it's falling to the ground. Does that make sense? As opposed to what happens at 2 seconds, since the velocity is positive, it is still climbing. Got it? Whew. Okay. Last one, last part. When is the cannonball at rest? So when I mean at rest, okay, what we're trying to say here is when the velocity is equal to 0. Okay? And it's exactly how you think, right? We need to find when S prime of t is equal to 0. So 50 minus 9.8. Come on, there we go. 50 minus 9.8 t, we need to find when this is equal to 0. We can solve this out. So, and I'm going to do it in my hot pink. Minus 50, minus 50. Negative 9.8 t is minus 50. I can divide by negative 9.8 to get it by itself, to get t by itself, right? And I get left with t is equal to 5.102 seconds. So at t equal 5.102 seconds, the cannonball stops moving. There we go. There we have it. All right, so now what I want to do, we have answers for all of this stuff, right? But if you guys took a look, I gave you guys all a QR code. So Now that we have all our answers, go ahead, scan the QR code, and I'm going to run through some of the work on the calculator that pops up. Okay, so I'm going to do a double screen thing. I'm going to split screen thing. There we go. Okay, so let me zoom out a little bit. Whoa. So I can get more of the, there we go. All right. So the first thing that we did for A is we constructed the kinematic equation, right? So we know what it is. I'm going to type in that function that's right there in the green. Okay, so 250 plus 50x minus 4.9x squared. There we go. Now I'm going to rearrange this thing a little bit. There we go. I'm going to move this over this way, pull this out a little bit. There we go. So hopefully everybody sees. This is the, we don't need the function to see the function. We need to see the graph. That's the thing that I really want to show you all. Okay, here it is. Bam, bam. This is the trajectory. The blue line is the trajectory of our cannonball. Okay? Got it? Okay. Now, I have it as f of x up here, so I can go ahead and go back over here. So let me go ahead and do find and interpret part B, basically, right? I need to find f of 2 and f of 10. I can do f of 2, 330.4, and f of 10, just real quick so that everybody can double check their work. Okay? Hopefully that makes a little bit of sense, right? Okay, now for C, that's where the QR code comes in real handy. I want to find the slope of the tangent line, right, at 2 and the slope of the tangent line at 10. Okay, that's what this calculator actually does. You guys see this A value that's right here. This is that point, and if you guys, let me zoom in, it's doing the computation for the slope of the tangent line, and it's giving you the slope. That's actually going to be the B, or sorry, the M that's here. Okay, got it? The B is going to be the other half. We'll take a look at that in a little bit. Not right now. We're more concerned with what the M does. Okay. So for M, I need it at t equal 2. So I'm going to grab this thing. I'm going to zoom out a little bit, and I'm going to move my A value to 2. There we go. Okay. And if you take a look, there's our M. M is 30.4. Okay. And just like we said in part C, right? At that point, for our cannonball, right, it is at 330.4 meters off the ground, and it is still climbing because our velocity, we found it to be positive. It is a positive 30.4, okay? Now, let's go ahead and do S of 10 and S prime of 10. So I'm going to grab my A value, and I'm going to move it all the way over to 10. There we go. Okay, so if you guys look, the height of my cannonball is 260 meters off the ground, right? And my velocity that I found is negative. So that means our cannonball is dropping, just how my graph is showing us, right? So basically, all is right with the world. Got it? Okay, now, last one, part D. Okay, when is the cannonball at rest? So that means when we say that the cannonball is at rest, when is it not moving? When is the velocity not moving? And you guys see how what we found was this, that the time is equal to 5.102, and it happens to be, look at that point up there. That is the highest point. That is the highest point of my cannonball. And that happens at 377.55 meters. Okay, so what we ended up finding when we set the cannonball, when we wanted to find when the cannonball was at rest, when the velocity is equal to 0, what we found there, right, was when it was right at the tippy top. Does that make sense? So at the very, very tippy top of its path, okay, the cannonball stops climbing and has to drop. Right? Whatever comes up must come down. That happens at 5.102 seconds. Okay? Now, let me maximize our notes again. There we go. Hopefully you guys see how useful this is. This is really the power of calculus. Okay? That using a particular function, right? We can now determine, right, the behavior in terms of rates of change of that thing, whatever it might be, right? If we're given its particular initial function. Does that make sense? So in this case, if we were given a position function for a cannonball, right? We can determine with real good accuracy the velocity at any point that we want, and its behavior at any point we want. Cool stuff, huh? Cool stuff. Okay, what comes up next is I'm going to make you guys do one. Okay, same idea. You guys are going to be doing kinematics equations. You guys are going to be doing derivatives and accelerations in this case, right? And you guys are going to interpret it all appropriately. Okay, we're going to do this in class. I'm going to give you guys a good chunk of time to do it. Okay, moving on though. Okay, what we just did is we used the idea of the derivative being an instantaneous rate of change, right, to determine the behavior of something. Okay, in the example that we just did above, right, we were given a position function and we were able to determine velocities, right? Okay, that concept of instantaneous rate of change as the derivative, right, is not limited to the position function. It can be used as the rate of change of anything that we really want. Okay, so as an example, okay, I'm throwing in a business example here. Okay, so the first one, suppose we had the cost in dollars for a company to produce X pair of new lines of jeans. And that equation is this right here. So this equation, if we make X pairs of jeans, okay, then C of X is going to give us that cost of making that many jeans. Okay, so A is asking us first, without doing any calculus yet, right? What does it cost to make 100 jeans? And this is exactly how you think it would work, right? So this means we have to do C of 100. Whoa. C of 100. So 2,000 plus 3 times 100, right? Plus 0.01 100 squared plus 0.00022222 100 cubed. Okay, and if you do this all outright, you should get 2,600. Okay, now interpret. I need to turn this into English, right? Okay. The cost of making 100 pairs of jeans is, whoa, $2,600. Done. This is good old regular pre-calc, right? I'm giving you a function, plug in the value, give me the output, and then turn it into English. Yeah? All right. We're good. We're good. Okay. Next one. Now we're going to be messing around with the calculus. Okay. Okay. Find and interpret in complete sentences this thing right here. So in the previous example, right, if we were given a position function, right, we were finding the instantaneous rate of change in the position, right? And we just so happen to call that velocity, okay? We can't call this a velocity, but we can still use that interpretation of the instantaneous rate of change in a cost. Got it? So this is going to be the instantaneous rate of change in the cost when we make 100 pairs of jeans. Got it? Okay. So it's exactly how you would think we do it, right? So first of all, we need to find C prime of x. We need to find the derivative of this right here first. So we need to find that derivative first, okay? The derivative of that is going to be the derivative of 2,000, that's 0, plus the derivative of 3x, that's 3, plus the derivative of 0.01 x squared, that's going to be 0.02 x, plus the derivative of 0.0002 x cubed, 0.0006 x squared. Bam. So that's our derivative, right? Okay. C prime of 100 is exactly how you think, right? We're going to grab 100 and stick it into our function C prime. Okay. So that's going to be, and I'm going to reduce this really quick. So it's going to be 3 plus 0.02x plus 0.0006x squared, right? Okay. 3 plus 0.02 times 100 plus 0.0006 100 squared. And if you do this outright, what you get is 11. Okay? Now, this is $11. Okay? Okay? Now I'm going to do the interpretation. Okay? The instantaneous rate of change at 100 pairs of jeans is $11 per jean. You see what I mean by instantaneous rate of change? It's not limited to positions and accelerations and velocities, right? We can use that idea of instantaneous rate of change in any context that we want, given that we're using the derivative to describe that instantaneous rate of change. Got it? Whew. Okay, last bit. And this is what's important. This is what's useful in the business world, okay? For part C, okay, use the answer from A and B to estimate C of 101. So let's say I want to find how much it's going to cost for me to make 101 jeans. Okay, now you can plug it in to the function. Perfectly fine. But I'm going to be using answers A and B to provide a decent estimate. Okay, and the way that I'm going to do that is this, right? C of 100 plus C prime of 100. This was the cost to make 100 jeans, right? And this was the instantaneous rate of change at 100 pairs of jeans. So essentially saying, if I make one more pair of jeans, how much more will it cost me? Does that make sense? 2,600 for making 100 pairs of jeans, plus the 11, right, for that instantaneous rate of change. So a good estimate for the cost of 101 pairs of jeans is going to be 2,611. Okay? Boom. Okay. So like I said, right, this whole section is concentrating more on using that idea of a derivative as a rate of change, an instantaneous rate of change, okay, to not only produce like I said, velocities and accelerations if you have applications in physics. But looking at the instantaneous rate of change of whatever your function is modeling as well. Okay? Whew. I believe that is it. Quick checks come up next. I'm going to give you guys, this is a biology example. Okay? We'll do these in class. And then lecture questions. Okay? If you guys got any questions on it, come find me during my office hours, come to the math lab, or ask during your quick check times. Okay? Besides that, happy studying.